All right, so thank you everyone for being here. This is our second Good Systems Smart Cities talk for fall 2023. This week we have Yiming Xu. He's a postdoc in the Urban Information Lab. He is officially a postdoctoral fellow with the School of Architecture at the University of Texas at Austin. He received his BE and ME degrees in Transportation Engineering from Tongji University. He received his PhD in civil engineering from the University of Florida in 2023. His research focuses on developing and applying data-driven methods to tackle challenging problems in transportation systems. Today, he'll be giving a talk entitled Real-Time Forecasting of Dockless Scooter Sharing Demand. With that, I will hand the mic over and looking forward to hearing what you have to say. You can go ahead anytime. There we go.
Okay, let me share my screen. Just a minute. Can you guys see my screen?
Yep.
Okay. Let's get started. Hello everyone. I'm so happy to share my previous research with you guys. And today I want to talk about real-time forecasting of Dockless scooter sharing demand, a spatio-temporal multi-graph transformer approach. And what is Dockless scooter sharing? It is actually an innovative transportation strategy that enables users to have short-term access to a scooter as needed. It has its advantages and disadvantages. For example, it is convenient, it is flexible, it is environmentally friendly, and it also has some safety concerns, and it may also cause some curbside violation. The thing I want to emphasize is that the Dockless scooter sharing is alright. It's an important supplementary to the existing transportation system, and scooter sharing has experienced an explosive growth in the past decades. In US, over 100 cities have their scooter sharing systems, and in 2021, people in US took 62.5 million trips on Dockless scooter sharing, and the explosive growth also brings some operational challenges. Firstly, the trip origin and the destination demand is unbalanced spatially and temporally. Therefore, we need, especially in the peak hours. Therefore, we need to relocate the vehicles in the city, and to this end, we need to know the future demand in each area so that we can make a optimal vehicle rebalancing strategy. Secondly, the vehicles need to be collected and recharged, and then dropped off in specific locations. And the future demand need to be known to determine the optimal drop-off locations. Therefore, the real-time demand forecasting for the Dockless scooter sharing system is important. We want to deal with this problem and to forecast the demand. It is actually a time series predicting problem, but we can do a prediction just based on the historical demand. But we also notice that some factors also associated with its demand, such as weather condition, like temperature and precipitations. And the other and also other category of variables such as demographic characteristics, pointer interest, and build environment. Therefore, we also want to include these variables in our model to do more accurate predictions. So here is our research question. Basically, we want to know how to accurately forecast the spatial-temporal Dockless good sharing demand. Formally, we want given a node correlation graph, a weather condition matrix, a historical demand matrix. We want to learn a function that maps historical demand to the demand in the next m time intervals. To deal with this research question, we proposed a spatial-temporal multi-graph transformer. The framework is here. The input of this model include the historical demand, the weather condition, and the 4 graphs, including adjacency graph, functional graph, demographic graph, and a transportation graph, and transportation supply graph. And the spatial variables are embedded in these 4 graphs. Then this input are processed sequentially by a spatial block, a temporal block, and a one by one convolutional layer to get the prediction. In the spatial block, we constructed a graph convolutional network based on the 4 graphs, and we use this graph convolutional network to process our historical demand. Then the output of spatial block is passed to the temporal block, where it is processed by a sequence of transformer blocks. At last, we use a one by one convolutional layer to process the output and get the prediction. I will talk about each block in the following slides. We use a transformer to capture the temporal dependencies in the processed historical demand. The transformer is actually a attention-based model, and it uses multi-hat attention to where several self-attention operation are conducted to capture the features of the input. And compared with other temporal models like CNN and RNN, the self-attention can capture features from each time step in the historical demand. That operation makes it perform well, but it is also computationally complex. And we use a graph convolutional network to capture spatial information from the graphs. So why we use GCN rather than CNN? Because GCN can handle graph structured data, but CNN can only be performed in Euclidean space. And the sensor block group or the sensor track do not have a regular spatial structure. So we need to use a GCN. And the GCN performs convolutional operation using a filter. And this filter is applied to each node of the graph to capture spatial dependencies between the node and its adjacent node. And as I previously said, that we constructed 4 graphs to further construct our GCN model. The graph, the four graphs that we use include the adjacency graph, the functional graph, the demographic graph, and the transportation supply graph. Here is how I construct these graphs. For the adjacency graph, it is simply if two areas are adjacent, there will be an edge between these two areas, and if not, there will be no edge between these two areas. And for the other three graphs, we constructed a correlation matrix based on the spatial attribute of each row. Then we set a threshold based on the previous study, and if the correlation between two areas is larger than this threshold, there will be an edge between the two areas. If not, there will be no edge between the two areas. And then we will get the four graphs that we needed to construct the GCM. So we perform the two case studies to validate our model in Washington, DC and Austin, Texas. For Washington, DC, the demand is aggregated into the block group level, and the time interval is 1 hour. We use 4 months data for training, 1 month data for validation, and one month data for test. And for Austin, the demand is aggregated to the sensor track level, and the time interval is also 1 hour. And we also use 4 months for training, 1 month for validation, and 1 month for test. And I want to emphasize that we have more data. We have more data, but we only use the data before the COVID-19 because the usage pattern will be different, very different during the pandemic and before COVID-19. Yeah. Here's a list of actual variables we included in our model. We have point of interest data such as a number of hotels, number of tourism attractions, something like that. We also have demographic data, such as population density, such as the percentage of wide population, such as median household income. And we also have transportation supply data, such as work score, such as transit stop density, something like that. We also have the weather condition data, including daily precipitation, average temperature, and wind speed. We compared our model with some baseline models, including some statistical model like the historical average and ARIMA. We also include some traditional machine learning model like the support vector regression, the gradient boosting decision tree around the forest, and the MLP. And we also include some RN-based model like GRU and RSTM, and we also include a transformer for transformer as a baseline. Besides, we also include some spatial-temporal models proposed by other researchers, just like the TGCN and the MC-STGCN model. And we evaluated this model using MAE and RMSE. Note that smaller MAE and RMSE indicate better performance. And we can see from this table, the proposed model has the best performance among all of the baseline models. We also conducted an ablation study to see the contribution of some component of our model. We can see from the ablation study actually examine the contribution of the component by remove it and evaluate the performance of the ablated model, and if the performance gets worse, it means that the ablated component contributed to the prediction result. And we can see from the table that when we remove spatial adjacency graph, when we remove functional similarity graph, or the demographic graph, or the transportation supply similarity graph, or the weather condition, the model becomes worse. That means all of these components contributed to the prediction of this model. And here are two. We also compared the ground truth and our prediction. We visualized it as presented. We selected one region in Washington D.C. and one region in Austin, Texas. We can see that the ground truth and the prediction are quite similar. And I want to note that there are several extreme peaks in ground truth, and our model captured these peaks very well, as we can see in these figures. Here is a summary. This model is actually a transformer and the GCN combination of transformer and GCN model, and we include some actual variables, including point of interest, demographic, transportation supply, and weather variable. And we conducted 2 case studies in Washington D.C. and Austin, and validated that our model have significant improvement compared with existing models. And here are also some open questions for the future research. Firstly, the model interpretation. Since we only use ablation study to examine the contribution of each component, it is a little bit rough. I think we can develop some more detailed interpretation method to interpret a model to see what actually happens in this black box model. And secondly, the dynamic spatial information. Since currently we just use some static spatial variables, such as the number of hotels in one area, the average household income in one area. But in some cases, these spatial variables can be dynamic. For example, some restaurants only open in 10 a.m. and will be closed at 10 p.m. And this restaurant can only impact the demand of distributed sharing in the operation hours. Yeah. Thirdly, the fairness. It is about an ethical AI problem. We want to know the fairness of our model, to see if our model the prediction of our model has similar accuracy in different areas. We do want that our model can better predict the demand in some areas with high income, but have low accuracy in some area with low income. Yeah, that's a thing. And I think this we can discuss this future works later, and to see what we can do in the future. Yeah, that's it. Thank you.
Thank you very much. We appreciate the presentation. I certainly have some questions, but I can, of course, hold back for now. If anyone else would like to jump in first, please go ahead. And if not, I just sort of wanted to ask, I know you spoke a little bit about the possibility of incorporating dynamic spatial information like restaurant hours or something, which are dynamic, during a specific set of time. But have you considered any sort of even more dynamic events, such as like a Super Bowl or a like large concert coming to town? Can that sort of be integrated into the model as well? Things that might not that change at such a drastic rate, only once every several years or something like that.
Good question. This is we actually consider this kind of thing when we develop our model. But for this research, we just excluded this event from our data. Because there will the usage pattern will be very different during the event, and if we take this kind of data in our training set, the model will be this will influence our prediction for the Euro times. Yeah. So my opinion is that we can develop another model, especially for this large event. And then when we want to predict the demand during the event, we use that model. And when we want to predict the ordinary demand during the ordinary hours, we use this model. That is my thought. Yeah. But for this research, we only focus on the ordinary times. Yeah.
That makes a lot of sense. Thank you.
Thank you, Dr. Xu. I have one question. I'm interested in the data set that you're using. Like, what's the temporal resolution of your data set? I say you use some historical information to predict.
The time interval is 1 hour actually.
Okay, 1 hour. So how long will you try to predict, like the whole day, or like?
The output can be adjusted according to your demand. We can predict in next 1 hour, next 6 hour, or next 11 hours, something like that. But we can see that our every model will have these drawbacks, which is for the longer prediction, the accuracy will be worse compared to the next 1 hour. So I only present the result for prediction for next 1 hour. But we can do next several hours. Yeah.
Thank you. I have one more question. Like, you're constructing some subgraphs by some thresholds, right?
Yeah.
Yeah. So I think it's similar to some graph attention networks. So it does similar thing, or like, do you think it will improve some accuracy or maybe make it easier?
Excuse me. What attention graphs?
Like, it has it can like set difference wise to different neighborhoods, like adjacent neighborhoods by its different features. So I'm not sure if it's similar thing here. So
I don't think so, but yeah, I don't think so. But I have some thought. Actually, I have some thought about these graphs. If you don't mind, I can talk about that. Is that at the beginning, we don't want to use this kind of static graphs. in our model. We actually we want to make it trainable, make this graph trainable to get the optimal graph to help us to construct the GCN. It is our primary source, but actually this, because these variables are static, and we need to we need to obey some rules from some previous studies. So we just make it a static graph, and we use the threshold from previous study, and that is this thing you see here. Yeah.
Yeah, thank you. I think that the concept like constructing some like dynamic things, like dynamic graphs, is really great. So yeah, yeah, that's really great. Thank you.
Yeah, thank you for your question.
All right. Well, if there's no more questions, I want to be respectful of everyone's time here on a Friday afternoon. Thank you very much for your presentation, Dr. Zhu. And I look forward to seeing y'all in the next Good Systems Smart Series talk next 2 Fridays from now. So long, everyone.